We come to our last presentation today, and I'm really happy to announce, because it will be given by Chris Davis, my handsome colleague. He's also working with H.B. Fuller, has decades of experience in the glass industry, and as he is too shy to give this presentation by himself, he got him some support from Kevin Yin from Eckersley O'Callaghan. And I think you both are going to talk today how important long-time thermal performance of IGU units are.
Sebastian, thank you. It sounds like I've got a man on my team. Okay. Welcome, everybody. We'll try and keep this fairly brief because we're the last standing barrier between you and the bar, so aware of that. Thanks to the guys at Glaston who've are delivering what threatens to be yet another epic GPD, so fantastic and really great to be here. I'm Chris Davis, so as Sebastian has already said, I work with the business development team Glass for H.B. Fuller. H.B. Fuller are the leading suppliers of adhesive and sealant solutions for glass and facade. And I feel very privileged because I'm sharing the presentation with Kevin Yin, who's the Technical Director Facade for Eckersley O'Callaghan. I don't think Eckersley O'Callaghan need further explanation, so really a great privilege to have Kevin with me. Okay, long-term thermal performance of insulating glass. Sounds a little bit boring. We got a group of retrobates together about 3 years ago to really examine our thoughts and what we considered to be the effective service life of glass. And as a little giveaway to the end of the presentation, it might not be dew point failure, however. Eckersley O'Callaghan and Kevin's team helped with dynamic modelling and understanding how the mathematical parts of a dynamic carbon model might work with our thoughts. Our friends at GlassCheck provided invaluable data on field testing, and NSG were integral in understanding glass behaviour and treatment. And our friends at BFRC, who are an approved body, helped with some of our material understanding. So what were our objectives? Our objectives were, it's a bit like three short stories stitched together with a conclusion at the end. And they might not necessarily be integrally related, but they are key to the end conclusion. So cavity failure, just understanding what are the consequences of the key components of cavity failure. Field studies, so how do those cavity failures manifest themselves in real time? So what actually happens out in the field and not necessarily our considerations as we would see it in a test environment, a controlled test environment, for instance. And then finally, how do we create a roadmap that will give us that gives you an accessible method of achieving what could be the baby steps towards a dynamic carbon model that considers the degradation of insulation materials in facades and buildings. Okay, this was driven from my many conversations with facade engineers and with architects, and this was the picture I got. Because that's how it is, isn't it? That's how it is. There is no gas loss, there is no change in centre pane U values, there is no need to consider that there may be a change in the building fabric performance. Yeah? Not really. So the green line would follow that train of thought. Actually, the potential for gas loss in cavities is evident. We know about this in the industry. And that relates back to a change in U value, a step change in U value. So if we take worst case scenario, which is the purple line, you can see that a gas loss of 100% to nothing. It's never quite 100%, as you know, but gas loss 100% to nothing results in a U value, a centre pane U value change shift of about 0.25 to 0.3 with a 416.4 low E unit. We do know about this as a standard calculation for it, so that's okay. We kind of got that. We've got that message. For our study, what we realised was actually there were two divergence points. So there's the green line, which is the bit that never changes, but actually that's represented by divergence point 1, which is where we get gas loss. And then that manifests itself in divergence point 2, where that gas loss becomes accelerated, and then we move towards coating failure. And that coating failure, again, is designated in EN672. So once the unit is saturated, then the coating performance, the emissivity performance, is considered to be 0. So that's set a landscape for us. So in summary, what we know is that gas loss has a significant impact on U-value performance. What we know from the material, understanding of the materials, is that the silver components in sputter-coated materials can react with silver and chlorine and deteriorate. And that pyrolytic hard-coated materials and sputter-coated soft-coat materials behave differently and react differently in those conditions. So we move on to our field testing. So understanding that those are the modes of failure and the consequences of failure, how does that actually manifest itself in real-time installations? So to do this, really important that we're able to go to site, evaluate gas concentrations, and with an accessible method, so not something that's just for a laboratory use, but with accessible methods and methodologies that you can use day in, day out. How do they influence IGU longevity? Is there a correlation between service life and gas retention? And use that data to investigate accelerated patterns of leakage, perhaps. So we took 2 data sets. You can't quite see it on there. One is a set of historic data with that, which our friends at GlassCheck furnished us with, and a set of specific project data measurements, which we took over a series of buildings earlier this year. The historic data tells us it was around about 1,100 individual units in buildings constructed between 2000 and 2024, and the message is that the results we got were anything between 1 and 90% of gas concentration. So very, very varied, and on average around about 59% across all the establishments and across all those units. And that's a range of applications, different types of buildings, retention systems, topography, regions, etc. In terms of our project-specific data, 5 buildings, all in London, with, again, very different retention systems, different construction periods, and different applications. And again, we saw a similar kind of pattern. 5 buildings, average gas concentrations. Bearing in mind we were only able to measure various parts of those buildings for accessibility, and each of those areas, which tended to be 1 floor, then we were able to evaluate around about 30% of the IGUs in those areas. But again, we were getting a similar pattern, sort of 40%, 37%, 42%, with the later buildings, 88 and 76. So the red line demonstrates, by the way, is where EN 1279 sets its bar at 80% minimum gas concentration. We also, as a benchmark, carried out some emissivity tests, and these were a little bit more interesting, I think. So we had standardized performances or results that we would expect for soft-coated glass at 0.03, and a range of results between 0.13 and 0.15, which would relate to the hard pyrolytic coated glasses. What we also stumbled across was a set of results that didn't really fit anywhere in between that. And that's raised some questions in our mind about the potential for some sort of staged degradation in emissivity at some point, and that will be part of further research that we carry on, but quite an interesting set of results. So the summary of the project field results were that we evaluated that visual inspections, are not sufficient to evaluate current state of thermal performance. Gas leakage is commonly observed, but not in all IGUs. So in some, but not all. There was some limited correlation between time and gas loss. And the vast majority of units tested didn't show visual evidence of degradation, so moisture condensation on one of the inner panes. What was key to us actually was that it was very clear that manufacturing quality, installation quality, play a massive part in terms of the longevity of IGUs in service. So with this knowledge, and this is the meat and drink of the project really, the bit that really was exciting to us, was how understanding how these things work is it possible to relay that information and cascade it into some sort of model that would incorporate that understanding of degradation. And would that then enable us to develop a better understanding of where that effective service life is? When do we need to replace an insulated glass? So I'll hand over to Kevin, because this is his part.
Okay, thank you, Chris. Yeah, maybe next slide. Yeah, as we know now, after Chris's talk, the slides, we know as a concept that the performance of the IGU thermal performance does change over time. And as a concept, we know the building energy performance as a consequence does change over time. But actually, how much does it change? So as an exercise for this project, we want to put something tangible, trying to quantify it. So we tried the dynamic modeling, trying to capture this change of the thermal performance of the IGUs. So for this exercise, we look at some theoretical models for different climate zone and different building types. Next slides, maybe. So for building types, we take the existing building models from the prototype models from Department of Energy of the US, and we selected the 3 building types, but also we made some adaptation to reflect the typical building stock in Europe in terms of the height of a building and the window to wall ratio. Also, we investigated the medium-rise office building, medium-rise residential building, and primary school single-story to represent a public building. We want to see how would that change impact on these different building sectors. So in terms of the climate zone, we looked at the 4 climate zones covering most of the Europe, and with the coldest to be very close to here. We got Helsinki, I think, because when we select the city, because Tom as a glass check, they are based in Helsinki. That's why we chose Helsinki there. Yeah, so for each climate zone, we have a set of assumptions of envelope thermal performance as a baseline to reflect the national code requirement, the general practice. Next slide. Then come to the IGU. We had a very theoretical assumption of how the gas will lose, the cavity failure, and what it might impact on the coating. We have to have a big disclaimer here. This is a very theoretical. The purpose is to investigate, have a feeling about what could happen to our buildings. It's not directly linked to the like a statistical data from the field testing. Probably that might be something we want to do in the next step. We need more data to analyze that to get the statistical behavior. So at this stage, we just use the theoretical, like a model of how IGU degrade. Next slide. So as a first step, we look at the best case and the worst case scenario, i.e. when the building is new at year 0 and at the 20 years, that's the end of our glass degradation. So we look at the operational carbon for including both cooling and heating loads. And you can see from year 0 to year 20, the operational carbon varies a lot. And the range or that variation depends on the climate zone and the building type. I guess it includes the the internal gains and the nature of the building, and also the glass window ratio. Then from here we can see the most visible difference is medium office. So for the following studies, we concentrated on this building type. So maybe next slide. So here we look at for the medium rise office building in the full climate zone. Look at so we say the glass will change, the thermal behavior will change. So how frequent should we really replace the glass? So we studied the accumulative carbon, including the lifetime carbon, including operational carbon accumulated over 50 years lifespan, and the embodied carbon related to replacing the glass at a certain intervals. And we plotted a curve, and you can see the optimum, based on that theoretical model, the optimum replacement of the glass is every 17 years. Rather than the typical practice is between 25 to 30 years. So in this case, okay, so we got that knowledge, so we actually trying to dive into okay, we got the optimum replacement strategy here. What happens actually to what's actually the gap between what we currently do by assuming the IGU as a constant performance, and actually the actual thermal performance of the IGUs. Next slide. So here on the right we have 4 plots representing each climate zone. The dotted line assumes the glass performance doesn't change, and it's replaced at the year 30. And we look at the accumulative carbon over the lifetime, up to 50 years. And this is generally what we do as consultants, as engineers, how we today design the building. Then we look at the other 2 lines, solid lines, and the red line shows if we replace the glass every 30 years, then you can see there is a gap between the theoretical design practice and what actually would happen. And that gap, again, varies, depends on the climate zone. Then we look at the green solid line is where we say, okay, if we replace the glass more frequently, even we included the embodied carbon for the replacement of the glass and the site operation, everything included, A1 to A5. So we got that you can cut down the overall lifetime carbon slightly, and this shows a way of analyzing that building more close to the reality as a first step. Yeah. So what we get from here, from this study is, yes, as a concept, there is a difference, but the gap is really depends on the building to building, and it needs to be a case-by-case study. From here, I hand over back to Chris.
Thanks, Kevin. So, project summary. There's a variance in IGU service, in IGU performance in service. Understanding failure modes is crucial for understanding energy efficiency and longevity. Product quality in terms of production installation is absolutely key to longevity. Performance decay clearly has an impact on carbon emissions of buildings over time. Dynamic carbon modelling can provide assessments of the performance of new building stock over time. And high performance coatings, providing that they're protected in moisture-free environments, are relatively permanent in performance. So gas concentrations measurements should be recorded for each IGU assembly is one of our recommendations as they're during manufacture. Marking schemes would be great because one of the critical problems we came up against when we do field surveying is a complete lack of O&M data, for instance, and understanding what we're actually measuring, so we have to try and assess that. There's a need currently to assess current protocols in terms of testing for sure, and TU Denmark have done a lot of work on that, and they have a paper to be released shortly, so that's quite interesting. Regular use of on-site monitoring for gas content could be incorporated into building quality assessment. And that's already starting now, and we're seeing much more focus on IGU concentration. IGUs can be designed to meet carbon payback periods, and that's all about that effective service life. And using proven and existing and new technologies is absolutely crucial in terms of starting to offset embodied carbon with operational carbon. But one of the key messages that came out from our work was that gas-tight, airtight, moisture-free environment is absolutely crucial for longevity, to keep those to keep coatings working effectively. And the good news is there are products out there that will do that. For us, this is one of ours. This is a reactive warm edge system, which we've tested to over 10 cycles of 1279 Part 3 without dew point failure. So it's out there. There is good news. And those are reactive warm edge systems, so they have a duplication, a multitude of benefits, including warm edge performance, but benefit from high performance chemical bonding to ensure that gas tight environment is maintained. But the key message here really is, where do we think we are in terms of IGU, in real-time IGU longevity? I suspect from our work that we're somewhere in that red box. We think we should be somewhere in the green box, but actually where we should be is probably the yellow box, and pushing on further beyond that. And that's the responsibility we have as processors, as designers, as glass manufacturers, to move rapidly towards that goal. Thank you very much. We've just slightly overrun, so I do apologise about that. But